Good morning, friends. Welcome back to the training session on Google Earth Engine and its application to water resources. I am Dr. Selva Balan, scientist CWPRS. So, we'll be continuing with the bathymetry extraction using GE and Python session. So, already we have covered how the session in the first session where how the bathymetry survey is being carried out, the limitations, the other methodologies, and how satellite derived bathymetry is going to serve the society in a large scale in the first session. Now we will continue with the part 2 where we will be explaining you the details of the analysis. Here I would like to thank all these technical partners who helped me in preparing this presentation, especially to Shyamaya Gode and Shri Om Pimpalgaonkar, Junior Research Fellow of CWPRS. We are very comfortable at this stage with the Google Earth Engine portal, and we have tried using all the modules, and we started using the code editor module and run a lot of applications so far. But this particular application where we will explain you how the bathymetry profile extraction steps are carried out. So we are you all aware that we are using Python API. We can use other APIs also, other application interfaces also. But Python has a link with Google with directly with Google Earth Engine as well as through Google Colab. So here we are going to demonstrate you with the Google Colab interface. Yes. So this is the sample screen how it looks like. But when we take up the presentation by hands-on, we can able to explain you in detail. The advantage of using Google Earth Engine is you need not install the libraries again. These are all pre-installed, and you get the workspace available, and you get a virtual processor available for you. Hence, you could be able to do the analysis in a global scale. So that you are already comfortable with, and you are aware also. So just to give a brief introduction about what we have learned in session 1, I have just kept this slide where you are seeing the bathymetry survey methodology where you have your vessel transmitting multiple frequencies, which in this case I have shown a dual frequency echo sounding method where the first frequency gives the surface and second frequency picks up the bottom. With the difference you could be able to get the sediment at a point with the GPS position being tagged at every instant. Actually at the point of interface you get lot of interaction, so the mathematics and the modeling which is taking place in the echo sounder is the strength of the signal being acquired, the quality of the signal being acquired. If you vary the frequency further down, you have an opportunity to go further beyond this. So which we have already covered in the session 1, calling it as a subbottom profiling techniques. Okay, in this particular presentation, we will be mainly covering the analysis procedures. So once the bathymetry data is acquired by a boat-based technology, this data is very useful for you to use it as a testing data for your satellite derived bathymetry. Even to come to that level, you need to go and do a lot of analysis using many other tools. In our study, we are going to explain you how QGIS, mostly we have used all the free software platforms, QGIS and Surfer modules used in the bathymetry analysis. So in this block diagram, you can able to see the first step is to load the bands. The bands here I mean is the satellite bands. So here multi-band satellite we are talking about. Especially we are mentioning about the European satellite where you have about 13 bands, and then we have to clip the region of interest because the imagery covers normally 200 square kilometers of area. So when you clip it to your region of interest, then the processing becomes simpler. The normalized differential water index will give you the land and water boundary. This particular data is very important because the survey may not have been carried out at FRL. So you can extrapolate the data up to FRL if your data collection is done in a proper planned way within the water body. Then we have to do the thresholding to remove the water body and the land portions. Then we will see how the raster to vectorization process has taken place, which is already been touched upon by other faculties, but still this is the stages we need to do in a practical approach to extract the processing data. Then we need to fix geometries. Then we want to remove the unwanted features. Here unwanted features in the sense the islands within the water body, or the river stream or the nalas which are joining beyond the cutoff point. By this process we extract a boundary file. This boundary file is used to superimpose over the data what we have collected through the boat based data logging. So now the data will be processed, gridded, and then it will be analyzed for the bathymetry profile, for which the boundary profile extraction is very crucial. With these steps, this is the step 1, which gives you the contour extracted from a satellite imagery from the multispectral data. But this particular output has lot of islands into it, so the processing will get affected if these islands are inside it. So you need to exclude the island portions. So that will be shown to you in the practical part. And finally, what we are interested in, drawing the contours. In this particular case study, this is at Mahi Bajaj Sagar Reservoir in Rajasthan, where Nuclear Power Corporation is coming out with the processing power plant, for which they want to understand the deep zones and the path through which the pipeline has to be drawn. So to get a powerhouse here, power plant here, we need to find out the deep packets. Then from superimposing the DEM over it, we could able to tell them the optimal path through which the pumping system, the pipeline has to be routed to the powerhouse. This is a 3D plot of the same, so where you can able to see the profile changes. Now here what we have shown you is, with the extracted bathymetry and with multi-band satellite data, we could able to produce the bathymetry even without surveying it. Like you teach the network with some percentage of data, and you can able to produce the output like this. Now let us see how the process, whatever the data what I am shown here is actually being carried out in the software using Google Colab, QGIS, and Surfer. Thank you. Now Mr. Om Pimplegaonkar will take out the session.
Thank you, sir. Thank you, sir. My name is Om Pimpargaonkar, and I will be taking you through the next topics, which are as follows: data downloading, data processing, implementation of machine learning, result, and conclusion. Firstly, we will begin with data downloading, for which we will be using the website, which is earthexplorerusgs.gov. Firstly, you need to create an account on the website, and after activation only you will be able to download the data. After logging in, select the address/place, type in the address, in our case which is Mahi Bajaj Sagar, click on show, and after clicking on this location provided, we just create a polygon around the region of interest simply by clicking around it. After putting a filter of month according to the Bathy analysis, clicking on datasets. For this analysis, we will be using Sentinel-2 data, which provides 10 meter, 20 meter, and 60 meter resolution multispectral images. Then clicking on additional criteria. In that, in cloud cover, selecting less than 10%. Clicking on results. Here we get lots of data set including and excluding our region of interest. By clicking on this footprint, we get the tile footprint, and by clicking on this image, we get the metadata which has the capture date along with few other parameters such as the orbit, the product format, processing level, resolution, image referencing, the zone, and other things. After going through these datasets and selecting the one which fits the better, just simply click on this download button, and clicking on the download, we get all the data which is 12 bands of various resolutions in a zip format. After this, I will be showing you how to import the data in QGIS and process it in QGIS as well as Surfer. After downloading the data and extracting it to the required directory, we get this folder in which we go into Granule, the first folder, image data, and over here we get all the band data from band 1 to band 12 along with RGB composite. Now we will process the bathymetry data in the software called as Surfer. So in Surfer, firstly we will grid that data into much higher resolution than the satellite data. So going into grid, selecting the raw data, bathymetry data, clicking on open. Then after analyzing the sample data, click on OK. Select the columns, gridding method. Over here we are going to use minimum curvature and the resolution, that is 5 meters by 5 meters. Selecting the output directory, renaming the file, and clicking on save. While this takes a little bit time, we will see the satellite data processing in QGIS. So in QGIS, click on layer, add raster layer. In that, in the file where we have the band data, granule, then image data, and then selecting the required band. We are interested in band 2, band 3, 4, 8. That's all. Only 4 band we are interested in. Clicking on open, add, and close. So here is the region of interest, and when you turn on and off, you are able to see the other band data. Now to further the process this data, we will be clipping it into a smaller region simply by going into raster, extraction, clip by extent, selecting the raster, and in clipping and extent we will be selecting draw on canvas and simply select the region of interest and giving the path for the new raster, which is band and band number, clicking on save and run. So here we get the clipped raster with region of interest. Now to clip the other bands, we will repeat the same process: raster, extraction, clip raster by extent. Only this time, instead of selecting draw on canvas, we will be selecting calculate from layer and the clipped layer. Providing the path, clicking on save and then run. Repeating this process for the other two layers, we get our final output, which will be further processed to calculate the water land boundary. After repeating the same process and clipping the raster to the region of interest, we have the clipped version of band 8, 4, 3, 2, which is the band 2 is blue, band 3 is green, band 4 is R, and band 8 is NIR. And deleting the original rasters, now we'll be calculating the NDWI, which is normalized difference water index for extracting water land boundary. Simply go in raster calculator, and just type in the formula, which is 3 minus 8 bracket close divided by bracket open 3 plus 8 bracket closed. After that, selecting the directory, we will save it as NDWI, and after clicking on OK, it will take few seconds. And here we get the normalized difference water index, where all the water bodies have pixel values greater than 0, you can see over here, and the land having pixel values less than 0. After calculating NDWI, now we will perform the operation of thresholding by simply going again into raster calculator, selecting the NDWI band using greater than symbol and 0, providing the path as, we will save it as thresholding, click on save and then press OK. Now what we get over here is all the water bodies have pixel values 1, you can see over here, and all the land bodies have pixel values 0, you can see it over here. Now we need to convert this raster into a vector with a tool called as polygonize, which is available in raster, and then conversion, raster to vector, polygonize. In that, select the thresholding raster, provide the path. We will save it as thresholding vector. Click on save. We are saving it as a shapefile, and then click on run. Now we have to delete the parts which are unwanted. For example, this way. So we'll simply select it, click on this toggle button, and then select features, click on the water body and click on invert selection, which will select everything other than the water bodies, that is the land bodies, and just simply click on delete. Click on yes. I will turn off the other layers, and over here we have a unfixed or non-regular water land boundary. Now click on the toggle button again, click on save, and now to remove the other parts such as this line, the small part, first we need to fix this geometry. We will use the tool called as fix geometry, pass this thresholding vector and provide an output path. We will save it as thresholding vector fixed, click on save and then run. Fixing geometries remove intersections, self-intersection, ring intersections. Then turn off the thresholding vector. Simply again go on toggle editing, select split features, simply draw a line along which you want to split the feature, left click, and then to end selection, right click. Then click on select features, select this feature and press delete. Don't forget to delete this small part also. Just simply select the water body, click on invert selection and then press delete. Similarly, we will get rid of this part also by going on split features, left click and right click to end the selection. Click on select features, select this feature and delete. And just for a safer side, again select the water body, click on invert selection and then press delete. Over here there is no other selection than the water body, so the delete option is not available. So that means there are no noise or no extra parts other than the water body. So just click on this toggle editing, click on save. Now we have the final water and land boundary in polygon format. Now we want the raster values, that is band values, only for the water body. For that we will be using a tool called as clip raster with polygon. Select the input raster, band 2, select the clipping polygon vector which is thresholding vector fixed, and output we will save it as B2 Sentinel. Click on save and run. This process might take time depending on your system. Just simply follow these steps for each band, and in output we get a band which has pixel values only for the water body area. As you can see over here, all the land part is removed. Simply follow this procedure for all the bands. After following this procedure for all the other bands, we have the final output where all the band values are only present for the water body. This is band number 8, this is band number 4, this is band number 3, and this is band number 2. After this, we will be processing the data collected by bathymetry, which we previously processed in Surfer, to create sample of measured data alongside the band data. Now we will import the graded data, which we graded using the Surfer software by simply going into layer, add raster layer. In that, select the grid file and click on open, add. First we need to clip this raster using the same tool, clip raster with polygon. Select the input date layer, thresholding vector fixed, and the output clipped Mahi data. Click on save and then click on run. Don't forget to set the CRS in which you are working currently for all the layers, or else the output won't be produced correctly. So this is the Mahi clipped data, as you can see, where each pixel value has the depth in meters. Now we will create a grid for sampling the Mahi data and all of the band data. For that, we will go into vector, research tools, regular points. We will select the input extent, which is B2 Sentinel. We will create a grid of 10 meters and save this file as 10 meter grid. Click on save, click on run. This might take a while depending on your system. Once this is completed, click on close, zoom this grid and overlap it on the band data. For now we will select band 2 Sentinel Over here, you can see all the points are on the boundary of each pixel. So to bring these points into the center of the pixel, we need to use a tool called as affine transform. In that, select the input layer, which is 10-meter grid. For translation on x-axis, as the sentinel data is 10 by 10 meter, we need to shift this grid with 5 meter in x-axis and 5 meter in y-axis. So 5 meter x-axis, 5 meter y-axis. You will save this layer as shifted 10-meter grid. Click on save. Click on run. This process also might take time depending on your system. Once this process has completed, you can see now the points are aligned to the center of the pixel such that each point will only have one pixel value. Now this layer extends beyond the region of interest, so we will use a tool called as clip. Select the layer as shifted 10-meter grid and overlay layer as thresholding vector fix. We will save this layer as boundary clipped Mahi data. Click on save and run. After the process is over, we can see over here that this point layer has been clipped to our region of interest. That is, all the land part is clipped out except the water body. Now we will use a function or a tool called as extract vertices. By passing the layer boundary clipped Mahi data, we will save it as vertices. Click on save and then click on run. Now when we click on any point, along with the other features, 4 to 5 more features are added, which are vertex index, vertex part 1, distance and angle. Now we will use a tool called as add geometric attributes to add x and y coordinates. We will select the layer vertices and save it as boundary clipped Mahi data with coordinates. Click on save and click on run. Once this is done, click on close, and when we select any point, we can see that along with the previous attributes, 2 more attributes are added, which are x coordinate and y coordinate. Now we go to the process called as sampling, where we sample the interpolated or the processed Mahi data, the bathymetry data which we processed in Surfer, and add samples of the bands, which are band 2, 3, 4 and 8, to the same attribute table. For sampling, we use the tool called as sample raster values. In that, as the input layer, we select boundary clipped Mahi data with coordinates, where we have each point with x and y coordinate. Now we need to attach those points with respected measured values. So we select clipped Mahi data, and for the new output column we select or we type measured, that means bathymetry measured. We save this as x y measured. Click on save and click on run. Once our data is processed, it is ready to be implemented using machine learning. For implementing this, we will be using Google Collaboratory Notebook, which is a cloud notebook. Over here, first we have imported required libraries, pandas for tabular data visualization and manipulation, NumPy for array manipulation and calculation, matplotlib for visualization. In the second part, we have uploaded the required dataset in the format x coordinate, y coordinate, measured, B2, band 2, band 3, band 4, band 8, and so on. And we have showed the first 5 samples of the dataset. In the next part, we have plotted the data just to have a visual representation. What are the ranges of our data? In the next part, we create a copy of our data so as not to disturb the original data. And according to the stump model, we add a column which we have mentioned as stump ratio, which is given by log to the base e of band 2 divided by log to the base e band 3. After that, we have visualized the whole data into first 5 rows and last 5 rows. In all, we have around 10,24,866 data points, out of which we will be using 80% for training and 20% for testing. In the lower part, we have plotted a scatter plot of stump ratio against the measured values. After that, we have splitted our data into training and testing. For training, we have used 80% of the data set, and for testing, we have used the remaining 20%, which goes to around 8,19,893 for training and 2,04,973 for testing. We have imported a machine learning library called as sklearn. In that, we have imported a linear model. In the next part, in that linear model, we have called linear regression, and after that we have trained it against the stump ratio as 1-to-1 training. In next part, we have performed prediction on the test dataset with few predictions to visualize. After that, to test or to find out the accuracy of how well our model has performed, we have used a R2 score matrix from sklearn.metrics, which provides us the accuracy. In the next part, we have plotted the measured versus predicted values. As you can see, we are very close to the actual measured and the predicted values. After that, we have imported one more model, multiple linear regression. In that, we have passed 4 bands, which are blue, green, red, and near to infrared. After training the model, we have found out the coefficients of each individual bands and perform prediction on that. using R2 score to see the accuracy, and plotting the measured versus predicted graph. Over here also we can see that measured value and predicted value are pretty much close. To save the model, we use the library called as pickle. We save the model called as finalized model, and we import that model again to predict the future test datasets. After adding the prediction column to the original dataset, we plot the predicted data values against the measured data values, either using Sulfur or using Python language in any notebook. So this was all about data downloading, data processing, machine learning implementation, result and conclusion. Thank you.